So our new topic is the so-called Poisson processes. Okay. So this is the first example of a continuous time stochastic process. By now we spent our time on discussing one very important class of discrete time stochastic processes, right? We discussed Markov chains in great detail. And now we are going to look at Poisson process. Then we are going to look at the continuous time Markov process. So this is one example of that, in fact. And it is also the building block for more general continuous time Markov processes. Okay, now the definition for this process, or the process of this kind, is the following. A continuous time integer valued stochastic process let us denote that by x and its value at time t by xt for every non-negative t, okay, is called a Poisson process with the non-negative, okay, with non-negative deterministic intensity process lambda, okay. So what is this? This is lambda, okay. Right. If the following two conditions are satisfied by this process, the first one is that process X has independent increments okay. And the meaning of this is the following. For every integer n greater than or equal to, okay, and for every real number, okay, we'll denote 0 by t0, t1, t2, and so on till tn, okay. The increments of the process X, okay, which are, okay, the change in the value of the process from time tn minus 1 to tn. Okay, n is fixed, so I better use ti, okay, ti minus 1. Okay, or maybe I should just write them one by one so that I don't have to worry, so I can discuss them in detail. So this is the change in the process from time 0 to time t1, right? And this is the change in the value of the process from time from time t1 to t2, right? You go like this. And finally the change in the process from time tn minus 1 to time tn. So if you take an axis, time axis, right, at time 0, you start observing this process, okay. Then we have time t1, pick t2, t3, right, like this. And we look at what? The change, the increment in the process from time 0 to time 1, from time 1 to time 2, from time 2 to time 3. And these are all supposed to be independent of each other. For X to be called a Poisson process, okay? So these are all independent random variables. Okay, but this is not enough. This is one of two conditions that we impose on a process for it to be a Poisson process. And the second condition is for every, okay, S non-negative and positive t, the random variable x at time s plus t minus x at time s. Again, what is this? This is the change in the process from time s to time s plus t. In the next t units of time, right, after time, starting at time s, this is itself, of course, a random variable, right? And it has a distribution. We want this random variable to have a Poisson distribution. Poisson distribution. So now this intensity process appears in the picture right at this point. In order to completely identify a Poisson process, we have to specify its mean, right? And we want this increment to have a Poisson distribution whose mean is given as an integral of the intensity of this process. Okay, lambda u du from the beginning of interval s to the end of the interval s plus t. Okay, right. And you remember how we calculate the probability mass function of a Poisson process, right? All these things can equivalently be written as what? The probability that this difference equals to an integer, non-negative integer k, let's say, given by what? So mean to the power k, in this case mean is given by this integral from s to s plus t of intensity lambda u du to the power k divided by k factorial times e to the same minus the same mean, right? So this is too large to put on as an exponent on this letter e. Instead we will use this notation. Exponentiate what? Minus the integral from s to s plus t of lambda u du. Okay? Okay, like this. So exponential of any f is e to the f. Okay, that's the notation we will be using. Okay. All right. And you can, so two conditions we never forget, and both of them are going to be very useful in doing calculations. Okay, one is the independent increments property of the process, and the other actually completely identifies a probability distribution of any one of these increments. Right? Take instead of stk, take instead of tk plus 1 minus tk, then you will get actually the probability distribution for tk plus 1 minus x at time tk. Right? So that is related to the intensity process. Right? In what way? We integrate the intensity over the interval from, in this case, it is going to be from tk to tk plus 1. Okay? We calculate, this is mean for the Poisson process, so mean to the power k divided by k factorial times e to the minus the mean. Right? This is the usual formula. You may ask why we have this complication here. It is actually, every complication to some extent gives also a flexibility to us. But to understand what the role or physical role of lambda t, we have to just play a little bit more with this thing. Take, for example, a small t. Let us calculate that probability then for any k. Okay? And let us then try to understand what lambda u has to do with this process. So for every small let me switch to delta t so we never forget that it is small. Okay? And let us try to calculate the probability that, right, over the interval from s to s plus delta t, the change in the process, right, given by this equals k. So if I use that formula, right, let me first just reproduce the same formula, then we'll simplify things, right? I have an integral, or the integral of the intensity process from time s to s plus delta t to the power k divided by k factorial times e to the minus the same integral. Right? Now, if delta t is small, then we can approximate this integral by what? The value of lambda at time s times delta t, right? So we have over the same interval from s to s plus delta t, we are given a function lambda u, right? So if delta t is small, right? So if it is small, perhaps we are in this range, right? And then we can just take the value of s. So this can be approximated closely as delta t goes to 0. So if you choose it small enough, is what? The height times the width, right? So we can just approximate, in this case, this integral with the value of this function at time s, the initial time, times the width of the interval delta t, right? So this is approximately true. So then we can simplify all these calculations. Approximately, this equals lambda s times delta t, right, to the power k divided by k factorial, and here we have e to the minus, right, lambda s times delta t, okay, and then we know that this can be written as what? 1 minus lambda s times delta t. So I will use this formula, e to the power x equals 1 plus x squared over 2, x cubed over 3 factorial. It goes like this, right? So I replace x now with minus lambda s times delta t. Then you will get, the next one is going to be just square of this divided by 2, right? And minus lambda s times delta t to the power 3 factorial. It goes like this. Right? So all of these terms, right, if you choose delta t very small, quite small, these numbers are going to be a lot more smaller than delta t, because you are taking the third power, or you are multiplying the same delta t with itself twice, 3 times, or 4 times. Right? It is like starting with 0.1 and you multiply with itself, you get 0.01. You multiply it 3 times, you get 0.001. It just quickly goes to 0. Right? So in any kind of approximation, then we tend to ignore these terms if there is this one. There is a term which is about in the size of delta t. If you compare all these terms with these, they are going to be very small. So we don't make too much mistake or the error is going to be small if you ignore these things. Okay, but in all these expressions, we still want to remember that we have a term, but we may ignore that at a later time because they get smaller terms in comparison to delta t. We just write small o of delta t. Okay, meaning that, well, this is some term that I really don't need to remember. All I need to remember is it is extremely small if you compare it with delta t for small delta t. For small delta t, right? And we started with small delta t. Okay? Okay, let me just then simplify. Now, instead of an exponential term, I have kind of a linear term here, right? So, for the time being, we can just keep this as it is. Okay? Times 1 minus lambda s times delta t plus a term which may neglect later. Okay? Then we can open this up, right? develop these terms, but in the meantime I would like to just see what the value of this probability, right? This is a probability for different k's. Now it is time to look at, for example, what this is when k equals 0, when k equals 1, and when k is 2 or more. When k equals 0, so this vanishes, this entire term vanishes, right? Something to the power 0 is 1, you divide by 0 factorial 1, so you get what? 1 minus lambda s times delta t plus a negligible term. Okay? So with this probability, with this approximate probability, if delta t is small, there will be what? The change, the value of process is not going to change over a small interval. Right? The value of the process is not going to change over any small interval with this probability. When k equals 1, then you get what? Lambda s times delta t, so this is 1, this is 1. Lambda s times delta t, you get 1. Then you get lambda s times delta t, well, lambda s squared times delta t squared, which we said actually before, right? It is in comparison to delta t is very small, so we can just add that term to this negligible part. Okay, so I don't care this smaller part. Okay, so then with this probability, we know that if the process doesn't change, right, it is going to change by exactly by 1. Okay, for every k 2 or more, what happens? So then you will start right from the beginning, delta t to the power something which is at least 2, and you then multiply with some other terms. The entire quantity is going to be negligible for us. Okay, for small t, small delta t. So this is negligible. Okay, so the picture is now like this. For small t, right, the process is going to either does not change, or if it changes by exactly 1 with these probabilities. And if you compare with this or that number, the following number, this is extremely small. Therefore, the probability that the process is going to jump, the value of the process is going to jump by a value more than 1 is going to be negligible. It's almost close to 0. This suggests that actually, if you look at the process over time, okay, so you will see times when the process changes by exactly by 1, okay, or it just remains the same. Okay, it will remain at 0 for some time, then it is going to jump to 1. It will stay at 1 for some time, then it is going to jump by exactly by 1, okay? It will stay like that for some time, then jumps again, right? You will see that the sample paths of this process look like this, okay? So on the y-axis you have process x, on the x-axis you have process t, right? Right? The argument works like this. So if you are close to any time where there will be a change over the next very small interval, right? The size of the change can be either or exactly 1, if you compare it with 2 or more. Okay, so you have a delta t, then all others are a lot more smaller, right? So that's the intuitive picture. That's the intuitive picture of this process x. Okay, it goes like this. So you have this is 1, this is 2, this is 3. Right? And in these formulas, you also see that the so-called rate or the intensity of the process appears. Right? You see that actually the probability that the process is going to jump over the next small time interval delta t is proportional with value lambda, which depends on the time when about the change is going to happen. Okay, therefore this is called sometimes the rate or intensity, actually the word that we chose from the beginning, okay, with which the process, okay, jumps over a small interval. Okay, over a small interval. Okay. Do we have any questions by now? Huh? Okay. Now, there are special cases of the definition that I just gave, right? If the intensity at any given value, at any given time s equals to the same constant lambda, okay, for every s. Okay. Then Poisson process is called a homogeneous Poisson process. Okay, and the reason is gonna be clear in a moment. Let me see. If I just want to make sure that I don't jump over any important thing that I should tell you before. Okay, if this is the case, we always, right? We said non-negative. Now, if it is a constant, the process will, I mean, this assignment will make sense only if lambda is strictly positive. Okay, if this is the case, then you look at this important quantity, right, which determines all the probability distributions, namely the integral from s to s plus t, okay, of lambda s times ds, right? Here, this is gonna be, so this is lambda. Right? Then the integral is nothing but lambda times dt. Right? This value, the mean of the Poisson distribution assigned to the distribution of the change in the process from time s to t plus s. Right? So this appears in the distribution of this random variable. Right? This thing now equals, if you just look at, okay, let me go back to this one, right? Okay. So now we can change this value here to just lambda t, right? Lambda t to the power k divided by k factorial times e to the minus lambda t, right? For every k. Okay. Now, if this is true, then we notice that this is true, which is, right, the first thing that you notice is that the probability is independent of time s, right? It only depends the probability depends, right, not to the endpoints of the interval s to s plus c, but the length of the interval, right? You have time s plus t, right? So we ask now actually, well, what is the change in the process over the interval from s to s plus t? In general, that may depend on both s and s plus t, right, through this integral. But if intensity is constant over the time, right, then we notice that this integral, first of all, is independent of s. So this is supposed to be the dummy, right? And the integral equals lambda times t, which is independent of s, but it depends on this on our choice of interval only through its length, which is t, right? So let's just take a note of that. Is independent of s and depends only on the length of the interval from s to s plus t. Okay, and for this reason, okay, For this reason, X is called a homogeneous Poisson process. Okay? And then you notice that if you just check what the distribution of random variable x at time t is, then we will see that they are the same as, it is the same as the distribution of the change in the process over the time from s to s plus t. Right? Namely, the random variables xt, okay, xs plus t minus xs and xt minus x0, okay, have the same, right? Have the same probability distribution. Okay? This is also going to be an important observation that we will be using a lot if we are dealing with the homogeneous Poisson process. Okay, let's look at a couple of examples just to illustrate how these two simple properties, defining properties of Poisson process, are helpful to solve problems. Okay, so this is exercise 1.7 from the new chapter from your textbook on page 275. Okay. Now, in this question, people use Poisson process to model the customer arrival process. Okay. So they say that the customers arrive at a facility according to a Poisson process having some rate lambda. Okay. They denote by xt the number of customers that have arrived up to time t. Okay? This can be just a bank branch, right? At Bilkent, let's say, they count number of people who walks in during lunchtime, or well, during lunchtime. That's fine. So over the next one period of time, perhaps, right? And we would like to calculate several probabilities regarding the number of customers who arrived over a specified time interval. Okay, so x in this case, xt, is the number of customers who enter the facility, right, until time t. Okay. And we are told that x is a Poisson process with some constant intensity, with some rate, right? With some rate, lambda. Intensity is then going to be what? Lambda times t, right? Intensity is supposed to be the integral of this over time. If it is just a linear function of time, then the slope is just called rate, right? Expected, and we know that this also corresponds to expected number of customers, or well, customers in this case, who enter the system per unit time, right? And we want to know the probability that there will be exactly one customer. Oh no, by time t, by time 1, until time 1. Exactly 2 customers enter the facility. In part B, we want to calculate the probability that until time 1, exactly 2 customers enter the facility, and till time 3, exactly 6 customers enter the facility. Right? In part C, we would like to calculate the conditional probability that there must have, or let me see, 2 customers must have entered the facility, given that if we know that exactly 6 customers entered the system until the end of time 3. Okay. And in part D, we would like to know the probability that 6 customers are going to enter until time 3 if we have already observed until time 1, 2 customers have already entered the system. Okay? These are the probabilities that we would like to calculate. The first one is easy, right? If X is a Poisson process with this given rate lambda, then what do we know? By the second defining property of Poisson process, for any fixed time t, at any fixed time t, xt is a random variable having Poisson distribution with rate what? Lambda times t. Okay, that integral from 0 to t becomes just lambda times t. When t equals 1, then we get the distribution for this, right? And x1 then has Poisson distribution with rate lambda, okay? And therefore this is nothing but lambda to the power 2 divided by 2 factorial times e to the minus lambda. Right? It's easy. Now how do I calculate this? 2 random variables. Do I know the joint distribution of these two? Perhaps, right? But at least at this moment I have to be careful that the random variables x1 and x3 are not independent. This is not just the product of the individual probabilities. Why are they not independent? They are not independent. Why? What is x1? Number of customers who entered the facility until time 1. So this is the number of customers who entered the facility until time 3. So this contributes into this, right? Because, right, you look at the time interval from 0 to 3, there is 1 and 2. So x1 counts the number of customers who enter the system here, and x3 counts the number of entrances until time 3. So they are not independent. Right? So this is then not the same as the probability that x1 equals 2 times probability that x3 equals 6. That's not the case. But what do I know about Poisson process X that I can use to find this probability? By
subtracting x1
from x3, because what do I know?
They are independent if they are not joint.
Right, that's great. Yeah, so we are going to use, right, in part B, we are going to use the independent increments property of the Poisson process, right? Use the independent increment property. So before you worry about the probability, you look at this event and you realize that this is the same as what? Okay, until time 1, exactly 2 customers enter the system. And for us to have exactly 6 until time 3, we must have exactly 4 customers to enter between time 3 and time 1. Right? We know that. And when you write it like this, now this counts the number of intervals over interval from 0 to 1. This counts, right, gives us the count for the arrivals from time 1 to 3. Right? Intervals are disjoint, therefore the increments of the same process x over these 2 disjoint intervals are going to be independent. Now I have every right, if you want to calculate now the probabilities, now I have every right to write this probability as a product of the probabilities of these 2 events, right? Times the probability that the difference between x3 and x1 equals 4. Okay? There I use the independent increment property. Right? Now I already know what this is. Let us write it again. So this is lambda to the power 2, right, divided by 2 factorial times e to the minus lambda, because this is Poisson distribution with mean lambda. Here, we can either use the original result, or we may just remember this observation, right? Okay. And this gives us basically what? This has the same distribution, has the same distribution as x2 minus x0, okay? And at time 0, I assumed that there were no customers in the facility, right? So this has actually the same distribution of x, the same distribution as x2, which is what? The Poisson distribution with now mean 2, okay? And then this is gonna be mean what? 2 times lambda, I should say, right? So this is distributed according to Poisson with mean 2 times lambda. Okay? We use this lambda times t formula. Right? Then therefore I have here to calculate this 2 times lambda to the power 4 divided by 4 factorial times e to the minus 2 lambda. Okay? Okay. So we know the answer for this one. Let's look at this one now. We can calculate part C by simply applying the definition of conditional probabilities, right? So we know that this conditional probability is the joint probability of these two events divided by the probability of the event to which we condition, right? Okay, we have that, but we already calculated, right? The numerator, it is this, and in the denominator we know that this thing now has Poisson distribution if we use the second property, defining property of process X. So this has Poisson 3 times lambda, right? Lambda was expected number of arrivals over a unit interval. Now I have 3 units of interval, so we multiply them. We never forget that. Okay. In the numerator, what do I have? It is lambda squared divided by 2 factorial times e to the minus lambda times 2 lambda to the power, okay, the difference, 4 factorial times e to the minus 2 lambda. In the denominator we have what? So the new mean is 3 lambda to the power 6 divided by 6 factorial times e to the minus 3 lambda. Right? Now here you see the exponential terms cancel, right, each other, and there is 6 factorial far below that just goes up. You get 6 factorial divided by 2 factorial times 4 factorial, right? Then what do I have? See, lambda squared, lambda to the power 4, you get lambda to the power 6. This lambda will cancel all of them. So there will be no lambda left in the final result. But then what else do I have? It's 3 to the power 6. Apparently there is 1 to the power 2, and there is 2 to the power 4. We can actually write all these things conveniently as 1 over 3 to the power 2 and 2 over 2/3 to the power 4. Okay? And in fact, you can recognize this as well. What is this? What kind of a combination it is? 6 choose 4 or 2. Let me write it as 6 choose 2. Okay? Do you recognize this formula? Huh? Binomial. So this is actually like what? Okay, let us first write it. This is binomial, probability mass function of a binomial distribution where you must have conducted 6 experiments, right? In each of which having a success, observing a success has probability 1/3, right? So what is going on here? Actually, this is you indeed have 6 experiments, okay, with in fact 6 arrival times, okay. And what are you doing with these arrival times? So 6 experiments with 6 arrival times are conducted, okay. And in this case, a success means, okay, let me see. Maybe I should be more specific. A success on the ith trial means that the ith arrival time falls in the interval from 0 to 1, okay? And therefore actually you are now counting, you are basically calculating the probability that exactly 2 of those 6 arrivals will fall in the interval from 0 to 1, and therefore you will have exactly 2 arrivals up to until time 2. As you, while you know that you have already observed 6 arrivals over the at 3 units of time interval. Okay, so 6 experiments with 6 arrival times are conducted, and is successful on the ith trial. In this case, means that the ith arrival time falls in interval 0, 0, 1. Right? So you have interval from 0 to 3, and you have 1 and 2. Right? So there are 6 balls in a sense, right? And each of them are equally likely to fall into any one of these baskets, right? And therefore you have the success probability 1/3. Success means that a given ball is going to fall in the first basket, right? And then this is like equivalent in this problem to asking that exactly 2 balls fall in the first basket, given that there are 3 balls that are going to be placed somewhere in this interval from 0 to 3. Okay? That's not a coincidence. We will see actually. We will state this computational result as an important proposition later. Okay? And we will be using it quite extensively as well. Okay? Any questions about that? About the interpretation? Right? 2 successes, 4 failures. So this is success probability. This is 1 minus success probability, 2/3. Everything just match each other in this case. Okay. And we have that result, the answer for part C, and then we can look at part D. Now, this is just the other way around, right? Here we know what happened at a later time, and then we ask what must have happened in the past. Here we have the other way around, right? Given that we already observed 2 customers, while 2 customers entered the system until time 2, what can you say about the likelihood that we will have exactly 6 customers entering the facility until the end of time 3 in the future, right? Again, we know that they are not independent. We discussed this earlier, we noticed that, but we can use the same trick. We will again use, to solve this problem, the independent increments property, right? So in order to have exactly 6 customers until the end of time 3, we must have exactly 4 customers in the remaining 2 units of time, right? In the remaining 2 units of time, from time 1 to time 3, there must be exactly 6 minus 2 arrivals. For this event to happen, right? The condition occurs on the same piece of information. So these two probabilities are the same. But then, independence of these random variables tell us that at this point, knowing that there were two customers, or the two customers arrived earlier, will give no more information about how many more customers can arrive in the any interval of time that belong to future. And this is therefore the same as the unconditional probability of the same random variable. Okay. And then we know that since we are dealing with an homogeneous Poisson process, the rate, the intensity is just a constant times time. So this has the same distribution as x2, right? Has the same distribution as x2 because x is a homogeneous Poisson process. Okay. This is not really essential, but perhaps you may find it useful if you have a lot more number of random variables around to calculate to worry about. And then we know that this is Poisson distribution with rate or mean, with mean lambda times 2 times lambda. Okay, and therefore this is now given as what? 2 times lambda to the power 4 divided by 4 factorial times e to the minus 2 times lambda. Okay. So the couple of examples that we are going to do at this beginning of this course or lecture will repeatedly use this independent increments property and that the increments have Poisson distribution. Okay? So that you never forget these two things. Okay? So let me look at another one. This is also an exercise coming from your textbook. Now this time we are interested in calculating. Yes? Huh? Is there a question? Is there a question also? Oh, okay. It is almost the time, huh? Okay, let us stop here because I know that you are anxious a little. Are you? I mean, the next example could have been actually related to the exam question as well.